All right, folks, welcome back. I left you with this. How would we go from this to, say, I'm just going to make one up because I'm awesome. Like that. I'm getting this question a lot. I'm seeing one of two things in people's responses. One of them is you would use, say, 1-bromocyclohexane. Now, this is problematic for a couple of reasons. One, this is secondary, so SN2 reactions are kind of weak sauce here. So there are problems there. Another person, plus I want to point this out, if this were the alkyl halide you use, 1-bromocyclohexane, your product would look like this. Which is not the target product that I had. So other people tried to use, say, this. Well, again, that won't give you the product I want. That will give you this. It does, however, take away the fact that you weren't working with a secondary alkyl bromide, because that's a primary alkyl bromide, but still not the product. What you need to do here is you would take this diketone, add base, usually sodium hydroxide, and 1, 2, 3, 4, 5, this. 1, 5, 1,5 dibromo pentane. Here's why. I'll do it on the next page because I'm out of room. I'm just going to start with the enolate here. Hopefully you can figure out how we got there. If not, ask me. I'll explain. 1, 2, 3, 4, 5. Br. Reform the carbon-oxygen pi bond. Nucleophilic attack. That was a lame line on one of the bromides, and you are here. One, 2, 3, 4, 5. Sorry, folks, I don't know where that paused, but this is where we are. Hopefully you weren't too far behind. Another base and gets involved, and you are here. Two, three, four, 5. 5 BR. And the second enolate would attack there, and you get this. Ta-da! There you go. All right, that's how you form these. Honestly, 5 and 6-membered rings are the best for this. Believe it or not, 5 is slightly better. Something to do with the angles and the geometry of that transition state. I have seen 4 used, where you can put a cyclobutane in between those two carbonyls, and it works. It's kind of hard, takes a long time. 3 is impossible, because the bond angles are just wrong. 7, the bond angles might be okay, but there are too many possible variations on a 7-carbon chain. So you get a lot of unreacted starting material or different reactions that can occur. All right? So this was alkylation this is the end of alkylation. Now we start talking about aldol. Formation and condensation. Aldol formation, your product is a beta hydroxy carbonyl. Your condensation gives you an alpha beta unsaturated carbonyl. This is done with ketones and aldehydes. Ketones and aldehydes. And the base you use in these is usually something like this, hydroxide. Yes, the equilibrium generally favors the starting material, but again, folks, when you're doing these, the thing to remember about equilibrium is even if 98% of it goes backward, 2% of it can go forward and form your product. Practically, this isn't that useful in a laboratory situation, but because we're just doing chemistry on iPads and paper and hopefully a whiteboard, or I miss the whiteboard. I miss being in front of all of you and telling jokes and having you laugh, because I really don't have any friends, and it's kind of lonely, and I really depend on you guys for my strength and my energy, and my life is really sad. So anyway, let's take a look at how an aldol formation works. We start, let's go back to our friend acetaldehyde, and sodium hydroxide. All right, folks, the way you can tell that this is an aldol reaction or an aldol formation is this. There's not another electrophile to be found anywhere around here, anywhere at all. So, what would happen, let me go ahead and show you the product here, because you know how I like to do that. There'd be the product. Now, I'm sorry, that is not the product, because we're doing a formation, not a condensation yet. My bad. All right, so here's the mechanism for it. Pull the proton off, forms the enolate. I'm going to say this one more time. Your book likes to show you the negative charge on the carbon. I like to show you the negative charge on the oxygen and the full formation of the enolate. You can do either one you want, honestly. I'm fine with it. I'm not going to count it wrong if you go with what the book does, as long as you don't bitch too loudly about what I do. I'm going to erase that really quickly because I don't have much room. All right, here's how this works. There's not another electrophile around. So, another one of these aldehydes will serve as the electrophile. Now, the issue here are people tend to forget there's more than one of anything in a reaction. Folks, we do not have monomolecular reactors yet. Oh, I long for the day when that's the case, because that would be really sexy. But until then, you have to realize you are dealing with bulk situations. That is more than one carbon. So now we are here. Then we pick up a proton from a water molecule, and we finally go here. And this is a beta hydroxy carbonyl. All right. What happens if we do this through an acid pathway? Same damn thing. Same damn thing. Here's what the product would look like. I'll run through this really quickly. What kind of acid do you want to use if you do not want a competitive nucleophile or electrophile running around in your system? Usually, you use sulfuric or phosphoric. They produce the least reactive counterions. So now here's your product. And there is the aldol product. Now this is from the acid catalyzed pathway. This is the aldol formation. All right, I'm at 10. I don't feel like talking really fast until 15, so I'm going to end this video here. When I come back, we're going to look at aldol condensation reactions, where we form that pi bond. So, see you soon.